So as I told you in the beginning, mechanism design is all about design of games. Okay, so this slide basically talks about the three legends of mechanism design. They got the Nobel Prize in 2007. So Leonid Hurwitz, who is no more, Eric Maskin and Roger Myerson. So we had the good fortune of Professor Eric Maskin giving a talk at the Indian Institute of Science in 2008, and he's actually coming to IISc almost every year, so since 2008. Okay, so I'll give you I'll start with this example for mechanism design, an example that is very, very familiar to you, and I hope you will be able to relate to this example very quickly. So here this is a standard cake cutting example. So what is the problem here? The problem is that there is a mother and there is a nice cake, and that has to be shared equally by the two kids. Now what can be done in a very natural way is the mother takes the best possible knife and then cuts the cake exactly into two halves and asks the two kids to take the two halves. Now it will happen that even if the mother has used the best possible knife and cut it into exactly two halves, each of the kids will go away with the feeling that it got the smaller of the two slices. It is very, very extremely natural it is. Now if the mother wants to solve this problem to the satisfaction of everybody, now a small game can be induced by the mother, and the game is the following. All that the mother does is to give the knife to one of the kids and tells the kid, why don't you cut this cake into two pieces, and tells the other kid, you have the freedom to pick, right, one of the two slices. Now what will the first kid do? The kid takes the knife, and before it cuts the cake, right, it will think about what the other kid will do, because the other kid is going to pick one of the two pieces. It knows that the other kid will pick up the larger of the two slices. So what the first kid will do is to cut the cake into exactly two halves, right, with the intention that when the second kid picks up one of these two slices, it will be just half and nothing more than half. This is what the first kid will do. So in the perception of the first kid, the cake is shared equally between the two kids. What does the second kid do? Now it looks at the two pieces. It will pick up what it thinks is the larger of the two slices, and the second kid is also very happy because it has picked up the larger of the two slices. But the first kid has cut it exactly into two halves, right? So you can see that social welfare is achieved to the satisfaction of everybody here. The mother is happy, and the two kids are also equally happy, right? Now this is an example of a simple mechanism. Now it is a mechanism design problem. What you have done is you have induced a game on the players here, so that the outcome of the game, so that an equilibrium outcome of the game maximizes the social welfare of the system, right? This may look like a very innocuous kind of an example, but it has far-reaching implications and significance. Just think that the first kid there is Mukesh Ambani, and this kid here is Anil Ambani. And what is the cake there? The cake there is the entire property. And who is the social planner? The social planner is their mother, right? It turns out that the mother actually was involved in making Mukesh and Ambani share that property, right? So another example could be that this could be the Karnataka state government, this could be the Tamil Nadu government, and the cake could be the Kaveri waters, right? So you would see that this simple example actually has a lot of significance, and in some sense this is a very canonical example for mechanism design. I'll give you another canonical example for mechanism design, and this is the story of one kid and two mothers. In the earlier example we had one mother and two kids. So here there is one kid and two mothers. And depending on where you come from, if you are coming from South India, right, I will say it is Tenali Rama, right? If you are coming from North India, I will say it is Birbal. If you are coming from abroad, I will say it is King Solomon, right? So what's the problem here? There are two mothers and there is a baby, and each mother is claiming to be the mother of the baby. Now this problem has to be solved by the king, and as usual the king can never solve the problems. He will always look at the minister, and the minister has to solve the problems. And in this case, how does the minister solve the problem? The minister says, in a very cruel way, the minister says, let us cut the baby into two pieces, and the two mothers can take away these two pieces. And then the minister closely watches the body language and response of the two mothers. The real mother immediately cries and says, please don't cut the baby. And then he also looks at the body language of the other mother and then declares that the real mother is the real mother. Fine. So you can see that here is an indirect way of eliciting the truth from the different players by inducing a small game. All that the minister has done is to induce a game between the two players, right? So this is another simple example for mechanism design. Now, what is mechanism design? So we have observed that you are inducing a game among the players such that in some equilibrium of the game, a desired social choice function is implemented. So you want to implement a socially optimal outcome in an equilibrium, and you want to implement it in the presence of strategic agents, self-interested agents. Fine. Okay, so this can also be called as the reverse engineering of games. So those of you who are doing software engineering will know what is reverse engineering. So mechanism design can be described as the reverse engineering of games. Now I'll give you a more serious example. This is the famous Vickrey Auction. Now what is this Vickrey Auction? William Vickrey got a Nobel Prize in 1996. He was alive when the Nobel Prize was announced, but he was not there to receive the Nobel Prize. He died right before receiving the Nobel Prize. And one of the outstanding contributions of William Vickrey was this auction. Now in this auction, there is a single indivisible object. It could be, for example, a painting, or it could be a camera, or whatever. There is only a single object, and then there are several players or several buyers or several bidders who are interested in buying this through an auction. And the auction mechanism is the following. The auction mechanism will expect all the bidders to come up with bids. So assume that the first bid is 40, 45, 60 and 80, right? And the auction mechanism tells you that whoever has bid the highest will be the winner. That's a very natural allocation rule. That's a very natural winner determination rule. But then the payment rule. So whoever has won this, so for example the bidder 4, because the bidder 4 has bid 80, is the winner of this auction. Now how much is this bidder going to pay? So he is not going to pay 80, but he is going to pay what has been bid by the next highest bidder. So if you know that you are not going to pay what you have bid, but you are going to pay something less than what you have bid, in fact you are going to pay what has been bid by the second highest bidder, then your strategy will be different. You will be more aggressive in bidding. And William Vickrey showed through a game formulation of this problem that it is a best response, it is an optimal strategy for all the players to reveal their true valuations. What do you mean by true valuations? When there is an object, you have a valuation for that object. For example, a camera. So my valuation for that may be 80, my valuation may be 60, or my valuation may be 45 or 40. In an auction, when I'm asked to bid, typically I will never bid my valuation. For example, if my valuation is 80, I will not bid 80. I may actually bid something less than 80 in a typical auction. But Vickrey auction tells you that you are going to pay something less than what you have bid. So now my bidding can become more aggressive. And what Vickrey showed very rigorously is that each player will now bid his own or her own true valuation. If my valuation is 80, right, it can be shown that it is a best response for me. It is best for me to bid my true valuation. So this is one way of inducing truth revelation. So if there is private information with the players, and if you want to extract that private information in terms of valuations and so on, so you can see that there is a simple allocation rule and a payment rule which will ensure that this private information is revealed, right? So what we'll try to do is to understand how revealing your true private information becomes a best response strategy for you, right? By formulating this as a strategic form game. So I would like you to pay a little more attention in the next few slides, because we would like to prove this result that Vickrey auction is actually truthful, right? Okay, so we are now going to formulate this problem as a strategic form game. So what's this collection of players here? You have 1, 2 up to n. In this case, it is 1, 2, 3, 4. You have 4 players. Then you have valuations v1, v2 up to vn. So you have 40, 45, 60, 80. So these are the valuations. So these are the values that the players have for that single object. Now what are the strategy sets? So here you have S1, S2, S3, S4, and all of them are 0 to infinity. I can bid anything. I can bid any real number greater than or equal to 0, right? So this is an example of a strategy set which is continuous, right? So you have an uncountably infinite set of strategies here, right? Now what is the allocation here? Allocation is highest bidder. So who has bid the highest here? The 4th bidder. So 4. What's the payment? Highest non-winning bid, or the second highest bid. Highest non-winning bid happens to be 60. And now let us look at the utilities. Now what do I mean by utility? You can see that what is the utility of player I. So a general expression for ui is xi. Xi will take the value 1 if player I wins the auction, and xi takes the value 0 if the player does not win the auction. So you multiply by either 1 or 0, and then you have vi minus pi. What is vi? Vi is your valuation, pi is your payment, right? So if your valuation is 200 and you pay 150, what is your utility? Your utility is 50, because it is 200 minus 150. So a generalization of that is ui is equal to xi multiplied by vi minus pi. Now in this particular case, what are the utilities? You will see that because player 1 does not win, utility is 0. Player 2 does not win, utility is 0. Player 3 does not win, utility is 0. But player 4 wins. And what is player 4's utility? It is 80 the valuation minus 60 with the payment, right? 80 minus 60 is 20. So valuation minus payment for winner, 0 for losers. So that is how you define the utilities here. So this way you have now formulated the Vickrey auction as a strategic form game with a set of players, a set of strategy sets, and then an allocation, a payment, and utilities. Now we want to show that for this particular game an equilibrium exists, right? In fact, it is something which is much stronger than a Nash equilibrium, called a dominant strategy equilibrium. We will show that a dominant strategy equilibrium exists where revealing or reporting or bidding your true valuation is an optimal strategy for you, right? How do we show that? So the way we show that is the following. Assume that instead of 4 players we have only 2 players. So we'll prove this result for only 2 players, and we will see how bidding your true valuation is going to be an optimal strategy for you. Okay, what is V1? V1 is the valuation of player 1 and B1 is the bid of player 1. V2 is the valuation of player 2, B2 is the bid of player 2. There are two cases here. What we are going to do is, we are going to compare V1 with B2. V1 with B2, right? Okay, so there are only two cases. Either V1 is greater than or equal to B2 or V1 is less than B2. These are the only two cases possible. Any other cases? These are the only two cases. Now we will analyze these two cases separately. Case 1. What we do in case 1 is V1 is greater than or equal to B2. This means the valuation of player 1 is greater than or equal to the bid of player 2. In this case 1, there are two subcases, 1.1 and 1.2. The subcase 1 is B1 is greater than or equal to B2. That is, the bid of player 1 is greater than or equal to the bid of player 2. The subcase 2 is bid of player 1 is strictly less than B2. These are the two subcases. If B1 is greater than or equal to B2, what can we say? If the bid of player 1 is greater than or equal to bid of player 2, what can we say? We can say that player 1 wins, right? So player 1 wins. If the player 1 wins, what is the utility? Utility will be U1 equals valuation of the player minus B2. Why is it B2?
The losing bid.
Yeah, because he is going to pay the highest non-winning bid or the second highest bid. So V1 minus B2 will be the utility, and we know that V1 minus B2 is actually greater than or equal to 0, right? So this completes the analysis of subcase 1. Let us look at subcase 2. Here B1 is strictly less than B2. What does this mean? This means that bidder 1 will lose. Bidder 1 will lose, which means U1 is equal to 0, right? Okay, so if we are in case 1 where V1 is greater than or equal to B2, either utility is going to be greater than or equal to 0 and equal to V1 minus B2, or the utility is going to be 0. Fine. So now let us look at the situation where the player 1 is actually bidding his true valuation, right? Bidding his true valuation also is a strategy for player 1. So if bidder 1 is truthful, what is B1? B1 actually is equal to V1 because the bid is equal to the valuation. But what is V1? V1 is actually greater than or equal to B2. So then what will happen to U1? U1 becomes V1 minus B2, which is the same as this V1 minus B2 greater than or equal to 0. Fine. So you will see that if you are bidding your true valuation, you are going to get a utility which is greater than or equal to 0 and equal to V1 minus B2, which in some sense is the maximum utility that you can get in all these cases. You look at case 1.1 and 1.2, what is the maximum utility you can get? That's actually equal to V1 minus B2. The same maximum utility you are getting by bidding your true valuation. Fine. So one way of saying is that, right, by bidding your true valuation, you are going to get your maximum utility. So bidding true valuation is a utility maximizing strategy for you. Fine. So, and this result is true whatever the values of B2, whatever player 2 is bidding. Fine. It is a best response for you. It is optimal for you to bid truthfully. This is case 1, right? Let us look at case 2. What is case 2? V1 strictly less than B2. Case 2, in case 2,
is this closed bidding or open bid?
Okay, Vickrey auction is called a sealed bid auction. It is called the second prize sealed bid auction, right? It's sealed bids, right? That is each bidder does not know the bid of the other player, right? Okay. Okay, in case 2 also there are two subcases. The two subcases again are B1 greater than or equal to B2, B1 is strictly less than B2. If B1 is greater than or equal to B2, what does this mean? This means bidder 1 wins. If bidder 1 wins, what is his utility? U1 is equal to V1 minus B2. But what is V1 minus B2? It is strictly less than 0. Right? So here is a case where your valuation is less than B2 and if you win, your utility actually is going to be less than 0. Fine. Okay. Whereas if you are looking at subcase 2.2, when B1 is strictly less than B2, bidder 1 loses, right? Because the bid of 1 is strictly less than the bid of 2. So bidder 1 loses. When the bidder 1 loses, what is his utility? It is U1 is equal to 0. So in the case where the valuation of player 1 is strictly less than the bid of player 2, what is the maximum utility that you can get? It's actually equal to 0. Now let us look at what will be your utility if you are truthful. If bidder 1 is truthful, your bid is going to be equal to your valuation V1, but V1 is less than B2, so you will lose and your utility will be 0, and 0 is the maximum utility that you can get in this case, right? So you will see that in both the cases that we are looking at, bidding your true valuation turns out to be a best response strategy for you or an optimal strategy for you. And in the language of game theory, this equilibrium actually is called as a weakly dominant strategy equilibrium, and it's a much stronger solution concept than Nash equilibrium, right? So this is how William Vickrey, using a very simple but extremely rigorous formulation of this problem, was able to show that through proper allocation rules and appropriately defined payment rules, you can actually extract truthful information from the players, right? So this is one of the very important aspects of mechanism design. In mechanism design, yes, you have a question.
There is a profit for the person who is auctioning the item, right? So he may not get the best possible cost that he's.
Okay, so here we are not looking at the revenue of the auctioneer, right? Okay, now that you mentioned, I will mention one result here. I hope I have those slides here. I may not be having those slides. Okay, now that you mentioned that, he's talking about how much of revenue the auctioneer will make. Fine. So there are 4 canonical auctions. If you are looking at a single object being sold, there are 4 different canonical auctions. One is called the English auction. The second one is called the Dutch auction. The third one is called the first price sealed bid auction. And the fourth one is called second price sealed bid auction. What we have just now discussed is the second price sealed bid auction, right? Now there is a famous result in mechanism design called the revenue equivalence theorem. What it says is that what is English auction? English auction is the usual open cry auction. So there is a bunch of bidders and there is an object in which they are interested, and one of the bidders will start with a very small price, 10. Another bidder will increase the going rate to 15. Another bidder may suddenly shout 20, 25, 30, 40 and so on, and it will reach a stage, right, where nobody else is in the fray, and let's say 90, and 90 is the final going rate, and that is the rate at which the object is going to be sold, right? This is called the English auction. Whereas the Dutch auction, very famous for flower auctions in the Netherlands, something that you can see in the KSRTC bus stand here, right? Somebody will bring a collection of used clothes. Mostly, he will say these are all new towels and so on, but they will be mostly used clothes. And he will say, I will give it to you for 200 rupees, right? And nobody will be interested. Then that person will say, I can give it for 150 rupees, right? Then he will say, I can give it for 120 rupees. So this is called a descending auction, where finally, when he shouts 20 rupees, then somebody who wants to get trapped, right, will buy those towels for 20 rupees, right? This is called the Dutch auction. The third type of auction is called the first price sealed bid auction, where the bidders will submit their bids in sealed envelopes, and then whoever has bid the highest will be declared as the winner, and the winner has to pay whatever he has bid. This is called the first prize auction. Now the second prize auction is the Vickrey auction, where the highest bidder will win the object but will pay an amount which is equal to the second highest bid. So you will see that the revenue equivalence theorem actually is the result which says that as far as the auctioneer goes, the expected revenue for the auctioneer will be the same in all these 4 auctions. Which of the auctions the auctioneer should use will depend on the context, will depend on the object, and will depend on how easy it is to implement any of these 4 auctions, right? So you will see that when we are talking about Vickrey auction here, our concern is mostly to extract private information from the players rather than maximizing the revenue for the auctioneer. Yes. Yeah.
Some case first.
Yes.
That V1 is greater or equal to V2, and V1 has to be less than or equal to V1, right?
Pardon?
The subcase 1, 2.1.
Yes.
V1 is greater.
2.1. Yes.
V1 is greater than equal to V2.
Yes.
And V1 has to be less than equal to V1, right?
B1 has to be less than or equal to V1? No. We are not making any assumptions about that.
You can like.
Yes, B1 can be greater than or equal to V1 also. See, for example, if it is a third prize auction, B1 can be greater than V1 because you know that you are going to pay the third highest bid, right? Your bid actually can be greater than your valuation. Fine. So we are not making any assumptions about the relationship between V1 and B1. It's a very general result. It's a very general result, and all that we are analyzing is the relationship between V1 and B2. That's all. And there are only 2 cases. Either V1 is greater than or equal to B2, or V1 is strictly less than B2. And in both the cases, we are showing that bidding the true valuation is going to be good for player 1. Right? Yeah.
Are 4 auctions the same? The results are the same?
The results say, the revenue equivalence theorem says that under what are called benchmark conditions, the 4 different types of auctions will produce the same expected revenue. The same expected revenue for the auctioneer.
I was not talking about revenue.
Yes.
I was actually, for example, in this one, the Vickrey
Yes.
scheme, you are forced to give your true evaluation.
Yes, yes.
And that's the best strategy. Would this be the same in all cases?
Okay, that's actually a very deep question. Now, when you prove the revenue equivalence theorem, one of the things that you will actually show is that the dynamics of English auction is the same as the dynamics of the Vickrey auction. Now, Vickrey auction is a single shot auction.
Yeah.
English auction is a dynamic auction. But the outcomes of these 2 auctions can be shown to be the same. And then you can also show that the outcome of the Dutch auction, the expected outcome of the Dutch auction, will be the same as the expected outcome of the first prize auction. Right? And in the case of Vickrey auction, revealing your true private information or true valuation constitutes a dominant strategy equilibrium. In the case of the first prize auction, revealing your true information is not an equilibrium. And there is no dominant strategy equilibrium. What exists is only a Bayesian Nash equilibrium. And you can show that in this Bayesian Nash equilibrium, right, your bid will not be equal to your valuation. So from that angle, the first prize auction is not a truthful auction, whereas the second prize auction is a truthful auction. Right?
In this,
yes.
See, this part is fine. If bidder 1 is truthful, then you will maximize.
Yes.
But it's clearly not only if, right? So
it is not clear. It's clearly not only if. There may be other strategies.
So B1, in fact, for B1 greater than or equal to V1.
Okay, so this is
the same thing will hold, isn't it?
Which one? B1?
For B1 greater than or equal to V1.
B1 greater than or equal to.
Case 1 and case 2.
Yes. Case 1 and case 2 will hold whatever the relationship between V1 and B1. Whatever the relationship between V1 and B1, both case 1 and case 2 will hold.
No. I'm saying that this final result.
Yes.
You will maximize your utility.
Yes.
Whenever B1 is greater than or equal to V1, isn't it?
Whenever
B1 is greater than or equal to V1. Not only when they're equal.
Not only when they're, yes, absolutely. So you can see there are 2 cases here. B1 greater than or equal to B2, B1 strictly less than B2.
No, I'm talking about B1 and V1.
B1 and V1.
Yeah.
Okay.
So
if B1 is equal to V1, you are maximizing your utility.
No, what about B1 greater than or equal to V1? I will still maximize my utility.
No. because you may not even, you may actually end up getting negative utility. Okay, let me summarize all the results. The result says that there could exist other equilibria. That is, not revealing your true information also could be an equilibrium. Actually, several other equilibria have been derived from the Vickrey auction. However, the only so-called weakly dominant strategy equilibrium is this. Now, equilibria are various types. The weakest form of equilibrium is the Nash equilibrium. In this context, it's actually called a Bayesian Nash equilibrium. That's the weakest. Now, the next one is called very weakly dominant strategy equilibrium. The next one is called weakly dominant strategy equilibrium. And the highest is called the strongly dominant strategy equilibrium. In this particular case, you can show that there exists exactly one weakly dominant strategy equilibrium, and that is precisely bidding your true valuations. Other Nash equilibria exist where you are not bidding your true valuation. They are also Nash equilibria, but because Nash equilibrium is much weaker than a weakly dominant strategy equilibrium, you can expect the players to be playing a weakly dominant strategy equilibrium. Mechanism design only tells you it is enough you show one equilibrium where bidding true valuation is good for you. Now, the way you design the protocol can take care of things in such a way that the players will be driven to play that equilibrium. You will assume that you have enough paraphernalia to make the players play to the desired equilibrium. Right? You have raised a very deep question, right? Because games can have multiple equilibria, and some equilibria are desirable, some equilibria may not be desirable, right? So you will require certain other paraphernalia to make the players play the desired equilibria. Right? Yeah.
You can analyze these also from primal dual perspectives, right?
Yes, okay. Primal dual perspective is very useful in the case of two-player zero-sum games. And in the case of two-player zero-sum games, you can actually show that the Nash equilibrium strategies of player 1 are precisely the duals of the Nash equilibrium strategies of the player 2, right? If you go to multiplayer, right, things do not carry forward that easily, but duality does play some role, right, in doing all this analysis, right? But in two-player zero-sum games, right, that was the contribution of Neumann and Morgenstern. They actually showed that the optimization problem of the row player is a linear program, and that is precisely the dual of the optimization problem of the column player. Yeah. Okay. Fine.
So,
yes.
In this, something in an auction, it's always a winner-take-all kind of scenario. Right? So
Auction is not a winner-take-all scenario.
In this case,
it all depends. So an auction contains two things. One is an allocation rule and a payment rule. What is the allocation rule? It is not necessary that you have only a single object. You may have multiple objects. For example, imagine a sponsored search auction. Now, in a sponsored search auction, against a keyword, there may be 10 advertisers who are interested, and there may be only 5 slots which are available on the right side of your screen. So now you have to decide which 5 of these 10 advertisers will be displayed on those slots, on those 5 slots, and which one will get the first slot, which one will get the second slot, and which one will get the fifth slot. This is called as the winner determination problem or the allocation problem, and typically that's an optimization problem.
does that only work when there are a finite number of objects or slots that, as you mentioned, or even if I have an infinite, like a set that needs to be partitioned?
Infinite number of slots is not a very interesting case. Because, see, infinite number of slots can be handled in games, but in realistic sense, right, it's not very interesting for us, right?
Cake cutting algorithm that you mentioned, cake cutting.
Yes.
Then your dominant equilibria there, dominant strategy equilibria.
Okay, so in the cake cutting example that I presented, right? So it turns out that the equilibrium there is a dominant strategy equilibrium, right? It's actually a strongly dominant strategy equilibrium. Fine. Now that problem becomes very interesting if instead of 2 kids, you have 3 kids, right? If you have a number of kids, the problem becomes very, very interesting. It actually becomes highly non-trivial also, right? Okay. So coming back to your question, right? Auction is never a winner take all, right? Auction will pretty much depend on what is the allocation rule, what is the payment rule, right? And these two together will decide who is going to win and how much is going to be the payment and how much will be the utilities of the different players. Right? Yeah.
But in this case, I thought you started by saying that the object being auctioned is indivisible. So in a sense, it is.
Oh, here, yeah, this is a single indivisible object. Yes, yes. Sure.
What does winner take all mean?
Winner take all means the objects are divisible, like in the cake. Like in the cake. Right?
Yeah,
So what happens is, what happens, let's say in the discrete case also you can talk about winner take all. So there are, let's say there are k units of a particular item, right? So the winner gets all the k units of that item, right? So it is, for example, the same advertiser will get all the slots in the sponsored search. That becomes a winner take all kind of situation, right? So this talks about properties of social choice functions. So any mechanism that you design is supposed to realize or implement a social choice function. What is the social choice function in the case of cake cutting? You would like the cake to be distributed, shared equally by the two players. That's the social choice function. So every mechanism implements a social choice function. Now, these are some desirable properties that you would like to have for these social choice functions. So the first one is called dominant strategy incentive compatibility. So what it means is that whatever is reported by the other players, it is always good for you to report your own true private information, right? Regardless of the announcement by the other players, it is good for you to reveal your true private information, right? So this is precisely satyameva jayate, right? That is, come what may, I am going to tell the truth. So this property is called dominant strategy incentive compatibility. It's an excellent property. It's a fantastic property because it's also called strategy proof. There is something very nice about telling the truth. If you tell the truth, you don't have to remember anything. It is strategy proof. If you don't tell the truth, then you have to remember the untruth that you have told. And in order to hide the untruth, you would have told a second level untruth, which also you will have to remember. And sometimes one lie will actually lead you to hundreds of lies. And you will have to remember all the hundreds of lies if you want to escape. Right? So this is not strategy proof. Whereas if you tell the truth, you don't have to remember anything. Yes?
This is assuming the first assumption that you have common knowledge systems. If you are looking at espionage networks, it's actually better to lie.
Where? Which?
Espionage networks.
Okay.
It's better to spread misinformation to improve your.
See, it all depends on what is private information here, right? What is not private information? What is common knowledge? What is not common knowledge, right? So in the setting that we are describing here, we will assume that the entire structure of the game is common knowledge. However, every player has some private information that only the player knows and the other players do not know. Right? So if you define private information that way, right, a mechanism which is dominant strategy incentive compatible will mean that it is good for every player to reveal his own true valuation or true private information, right, regardless of what the other players do, right? Okay, so the weaker form of incentive compatibility is called Bayesian Nash incentive compatibility, right? This is weaker, right? That is, reporting truthful information is good for you whenever all other players are also revealing their true information. It is much weaker than dominant strategy incentive compatibility. Now, there is a property called allocative efficiency which says that you allocate the items to those who value them most. Fine. Whoever has the highest valuation for the objects, right, those are the winners of these objects. This is called allocative efficiency. And budget balance means that payments and receipts are going to be the same in the market, right? And you don't need any external funding to be used for the market itself, for sustaining the market. Then there is a property called the non-dictatorship, which means that no single agent is favored all the time. There is a property called individual rationality, which says that it is if a player participates in a mechanism, his utility will never be less than 0, right? A player always has a non-negative utility by participating in the mechanism. So these are some properties of social choice functions. Now mechanism design theory will tell you which combinations of these properties are possible. Obviously not all properties can be satisfied simultaneously, and there is a series of possibility and impossibility theorems which will tell you what is possible and what is not possible. So some of these theorems are summarized here. Yes.
Yeah, the allocative efficiency.
Right.
Isn't that what all auctions are supposed to do?
Okay, so all the examples that I have given are allocatively efficient, right?
So is the distinction between value and bid? So value in the sense how much.
There's a difference. There's a difference. So value.
How much actually bid?
Yes, yes. So bids are always different from valuations.
So is that what is key there?
Yes. So in other words, value is private information.
Yeah.
Right?
Okay.
So when you do the allocation, you should allocate it to the players who value them most.
Right. Okay.
That is allocative efficiency.
So the more precise statement would be an auction by design guarantees that the highest bidder takes it.
No, no.
Not necessarily the highest value, right?
Not necessarily the highest value.
Okay.
Correct.
Okay. So which
But
is
if
what this would guarantee? If
Yes, yes. But Vickrey auction and first prize auction, they are also allocatively efficient, right? Okay. Okay, so as I told you, there are many possibilities and many other impossibilities. I don't have time to cover all of these, but I will show you a diagram which will, okay, so this also I'm going to leave now. I'll just show you one diagram which will tell us what is this mechanism design space, right? Now this slide will tell you that mechanism design is a very intricate subject. Now you have these host of properties. Only certain combinations of these properties can be satisfied thanks to these possibility and impossibility theorems. And if you are looking at the entire mechanism design space, you will see that the largest class of mechanisms satisfy this property called Bayesian incentive compatibility, which means that truthful reporting is good for you whenever all other players are also truthful. As a very special case of this, you have dominant strategy incentive compatibility, where revealing truth is always good for you, regardless of what the other players are doing. Now, if you want your mechanism to be allocatively efficient, now you will see that there are mechanisms which may not satisfy DSIC but may satisfy allocative efficiency and so on. And then if you are interested in what is called the weakly budget balanced property, that is the space of all weakly budget balanced mechanisms. Then the so-called strongly budget balanced mechanisms will be sitting somewhere there. And then you have what are called ex post efficient mechanisms. Then you have individually rational mechanisms. And then you have another class of mechanisms called DAGVA mechanisms. So now you can see how the space of mechanisms is now becoming more and more complicated. And you always start with a physical problem, and for the given problem you will try to identify what is the ideal set of properties to be satisfied by the mechanism. And now you take a look at this picture, and now you will figure out whether this combination of properties indeed can be satisfied, or what is the maximal subset of properties that can be satisfied. So mechanism design is more of an art rather than a science, right? In spite of the fact that there are impossibility and possibility results which are available in mechanism design. Okay, the summary of this slide is that mechanism design is a very interesting subject to study, and you can take any problem involving strategic agents and identify what you would like a protocol or a solution to that problem to satisfy, and this will help you to tell you whether these properties are indeed satisfiable. You can always identify a subset of these properties that could be satisfied, right? Okay, so I have no time to cover this. I thought I will present two interesting problems in mechanism design. And let me just say that there are many interesting challenges. One of them is to is to fuse machine learning, optimization, and mechanism design in the context of problems. Mechanism design is closely related to optimization. And it turns out that machine learning is going to play a very important role in making mechanisms work. So fusing all of these three is a very interesting research direction. There are lots of modeling issues. It is not very clear how a given physical situation can be converted into a game, and mechanisms can be designed there. There are lots and lots of computational issues. For example, computing Nash equilibrium is a grand challenge problem in computer science these days. Then making the solutions user-friendly is also equally important. Vickrey Auction is very nice. It will tell you that all that the agents have to do is to tell their truth, right? But not all solutions may be so simple, right? How can you come up with mechanisms which can be easily understood by the different agents, and you come up with protocols which can be easily followed by everybody. Okay, so this was a monograph that we put together in 2010, and this is the book which will give you more details, and these are some references. I'm going to leave the slides here, and these two websites have a lot of material on game theory and mechanism design, and I have to compliment all my students. So in putting together this presentation, I have done a lot of crowdsourcing. I have actually done expert sourcing. So these are all my students who have worked with me in the last 7-8 years, and they are the backbone of what all research has been done. And I will close with this marriage, which is very crucial for the so-called big data problems, or the so-called web-based problems, or the so-called modern problems. So let me end by saying that computer science and game theory, if they come together, will make a fantastic combination, and they have the potential to solve most of the interesting problems arising in the modern internet era. Right? With that, I will close. So thank you very much. If you have any questions, all the answers can be found in this book. Thank you.